So so let's talk about emission spectrum, and the other one is the absorption spectrum. Okay, so let's talk about the hydrogen atom. Say this is the proton at the center of this circular path. Okay, so you know that there are a lot of quantum states for an atom. So we know from the previous scenario that say this is the proton at the center, and electron could be in any state. Say for example, it could be in the ground state, and it's equal to 1. This is the ground state, and it has the lowest energy. It could be in the n is equal to 2 second orbit, second quantum state, or we called n is equal to 2 as second orbit, or we can also call it the first excited state. And say the electron could be in third orbit, n is equal to 3. It could be third, it is called third orbit, and it is the second excited state. Okay, so if electron jumps from high energy level, so they have high energy level to the orbit at low energy level, it will going to release the energy. Okay, so change in energy, either going from high to low or low to high, will be S times F. Okay, so where F is the frequency of emitted photon, or it could be absorbed photon. Okay, photon. Based on that, let's say we have say this is your ground state, ground level. Okay, ground state, and it could be any excited state. It could be n is equal to 2, n is equal to 3, or anything else excited state. Okay, say it is n is equal to 2, for example, and ground state, this is n is equal to 1 in our case. If the electron is in the excited state, in this state, then in this case, if electron jumps from high energy level to the low energy level, it will emit a photon of frequency S times F. Okay, this is the energy of photon. So in this case, this energy emitted will be S times F, which will be equals to, say, it has energy E higher and E lower. Okay, so it could be EU minus EL equals HF. So in our case, it is E2 minus E1 equals H alpha. Okay. So this particular frequency and particular wavelength of light, photon is emitted in this case. So this is the case of emission. Okay, this is the case of emission, means photon is emitted in this case. The other way around, we can think the same situation but slightly different, in the way that now we have the electron at the ground state. Okay, ground state. If we supply the external photon of energy S times F, then it absorbs this photon, then it could jumps to high energy level. So it absorbs, the electrons will absorb, then it will jumps to high energy level over here. Okay, over here at that point. So it go from ground state to the excited state. Okay, as before. The only difference is that here electrons, these electrons, the electron absorbs the energy E, which is equivalent to, which is equal to E U minus E lower, and jumps to excited state. Okay, here just in this case emits energy HF, which equals to EU minus EL, and jumps to lower energy level, or in this case ground energy level. Okay, ground state. So this is a case of emission, and this is a case of absorption. Okay, so if we use this concept to understand emission spectrum and the absorption spectrum, let's see, this is the source of the light. It emits all colors. This is the source of white light. So it emits colors of all visible, in this case visible wavelength. So color is white. Okay, it passes through a gas atom absorbs that energy, but you know it will not absorb all colors. Means the difference is that the gas atoms do not absorb all color, because we know that to have the absorbed, we must have to follow the condition that energy absorbed or energy gained must be equals to S times F. Okay, this condition must be fulfilled. So it will not absorb all the all colors, but only selected one, following the rules. Delta E must be, energy difference must be equals to S times F. Okay, so that's why if this white light passes through a gas, then the gas atom absorbs certain light, which frequency and wavelength get absorbed. It appears as black lines in the spectrum. So this kind of a spectrum is, we can see, we call the absorption light. So absorption light is not a new thing, but only those frequency which is actually absorbed by the gas atoms. Okay, in the emission, the case will be the similar. Only difference is that in this case, in the emission, if from this gas tube will emit selected colors of light. It will not emit all lights as before. This means it cannot absorb all light, all colors. It cannot emit all colors. So here we can see a few colors. This is called the emission line. So emission line and a spectrum line is a characteristic feature of atom. So if you consider in terms of frequency, they will be the same. Okay. So this is the concept behind emission spectrum and the absorption spectrum. Okay. So let's see one example over here. Okay, we can see some example over here. So in this slide, just we are explaining what we observe, and absorption spectrum is observed when light passes through a gas, this spectrum appears as black lines that occurs only at certain wavelength. This is the important point, certain wavelength, I mean certain frequency on the background of the continuous spectrum of white light. The missing wavelength tells us the wavelength of the radiation absorbed by the gas. Okay, this is all about this part, first part. Okay, in second part, the emission spectrum is observed when light is emitted by the gas. So gas will not emit all lights. This spectrum is seen as colorful lines of the background. Okay, so this is all about emission spectrum and absorption spectrum. So for example, hydrogen, we can see four distinct lines, emission spectrum, because this lies in the visible region. So you'll see here only 4 lines are visible to human. There could be many because we can see those lines. Okay, but there are many, the lines that are wavelengths shorter than 4,000 nanometer appears in the ultraviolet part and are invisible to human. There are infinite many invisible spectrum lines in the stage of hydrogen. So this particular frequency, particular wavelength is the emission spectrum, or we can get the similar frequency in the absorption spectrum. Okay, so let's see the one simulation over here. Say for example, I have here for the hydrogen, just you saw now, this is for the emission spectrum for hydrogen. So you see there are 4 colors that lies in the visible spectrum. If you want emission spectrum for the helium, we have 1, 2, 3, 4, 5, 6 lines we can see. Okay, for other elements, say lithium, again we have different colors. For sodium, we have only clearly mentioned 4 spectrum we can see in the visible region. For mercury, again we have different colors, different frequency. For neon, again we have different. Okay, so each element has their own emission spectrum. Okay, means they cannot absorb all kind of photons. Only given photon can put them from lower energy level to high energy level, or from high energy level to low energy level. Okay, so this also explains the Planck's hypothesis. So let's talk further. We have about the dual nature, about the dual nature of this electromagnetic wave, light, or any object. Okay, so dual nature means sometimes it will show the particle nature, and sometimes it will show the wave nature. So it will show sometimes particle nature, sometimes it will also the wave nature. Okay, but they are the equivalent concepts. So for example, just this is a recap. For a particle, is any particle of mass m moving with speed v, we have lambda equals h over momentum, h equals mv. So this lambda we know as before, this is called the de Broglie wavelength. De Broglie wavelength of the particle. Okay, and this is the p is the momentum of the particle, Okay, we know that for the photon, energy is associated, this energy of photon is associated as S times F. So E is the energy of photon, energy of a photon, and this F is the frequency of the photon. Okay, so the all particles will also exhibit this nature, what is called the dual nature, wave nature and the particle nature. Okay, so in the case, similarly, the electromagnetic wave, X-rays, and electron is the particle. You know that this X-ray is the rays and electron is the particles. Beam is actually diffract, so it's showing the dual nature. Okay, so you know that this is a wave, X-rays are wave, and this is a particle. We saw before that X-ray is going to diffract, so electron is also diffract, means electron showing the dual nature. So in this case, dual nature of electron means electrons behaves as a wave, and also the electrons behaves as a particle. So if you remember, in the case of the X-rays, we have, if you remember, we have the atoms are arranged in different planes. Okay, this is the interatomic plane, so we know this distance is d. We call it interatomic distance. Okay, and we pass the particular light wavelength. Say this light has wavelength, given wavelength. Okay, so it could diffract from this particle. Okay, then it will, if you remember the previous case, it will diffract like this. So this is the kind of diffraction phenomenon, and we know that for the constructive interference we have 2d sine theta equals m lambda. Okay, for the constructive interference. Okay, so we observe this phenomenon in the case of the X-ray. If X-ray actually going to diffract, same way we can say that electron will also be going to diffract. Okay, means this is the dual nature. So this experiment is called the Davison-Jarmor diffraction experiment for electrons. So what this does, that this coil is heated by this battery. So electron gun, what they do is that this filament produce heat. This filament produce the electrons. Okay, so you see this produces electron, and these electrons are speed up by accelerating potential difference at delta T. The whole system is called the electron gun. This means the electrons coming out through this electron gun will have a specific value of the speed. Okay, so this electron moving with the certain speed v. Okay, these electrons moving with certain speed with v, I represent by small v, it will hit a metal target. Then their electrons, actually what will happen, diffraction happens here. Okay, diffraction happens at this point. Okay, electron scatter in different way, but at a particular value of angle we can observe this diffraction phenomenon. Okay, so let's do some math over here. Okay, so let's do some math to figure out. So say, for example, in this experiment, the potential difference of the accelerating PD is represented by delta V. Let's do some math. So in this experiment, potential difference of accelerating source, okay, so can be written as, from electrostatics, it will be work done per unit charge. Okay, so we can rearrange this as work done equals charge. This is the case of electron, E. Potential difference of the source we represent by a delta V, if you remember that. So here, this is we are talking about the electrons emitting from here. Because of this speeding, this accelerating potential difference, it will speed up. Okay. So this work done is basically energy. So now the electron is moving, so it has kinetic energy gain. So we can write kinetic energy gained by electron equals E times a delta V. Okay, so kinetic energy, we know that this is half, gained is half mv squared, because initially electron is at rest. The electron is at rest if no accelerating PD has been applied. So this equals E delta V. Okay, so we can just going to rearrange that. So I'm going to rearrange as this half m squared p squared over m. You see that? Because these two are this expression and this expression are the same. Okay, then it equals E times delta V. Okay, so you know that this is P is m times P, so I can write this as P squared over 2m equals E times delta V, because P equals basically m times P. Okay, I can write like this. So if if I'm going to rearrange, I can write P equals 2m times delta V, and it goes under square root. Okay, so I got this expression by solving the equation for this picture. Okay, this means after coming through that, it has a speed V given by these equations. Okay, so the point of finding P is this. Then in the experiment, we know that this experiment is basically the experimental proof of lambda equals h over mv. Okay, this is the main goal. So this is p, small p. Okay, so lambda equals h over p. So, and it also says, as before, matters behaves as a wave. Matter, in this case, electron behaves as wave. Okay. So let's move further in our case. So we want to use lambda equals h over m times p. So this is basically h over p. So lambda, we can plug the value of p from previous part. So it will be under square root 2m e times delta v. Okay. So this will gives you, this gives theoretical value of lambda for electron. Okay. This equation gives, so we know if this is the case of diffraction, we can write, if this is the case of diffraction, we can write d sine theta equals m lambda. Then d sine theta, m, this lambda is replaced by h over under square root 2 m e delta v. Okay. So this gives the condition for maximum intensity. This means from the experiment, okay, from experiment, we can find theta and compare with above theoretical value. Okay, we can find that and compare. So if this is from theory and we can also record the angle from the experiment. So theoretical value and experimental value is found to be the same. So in my case, I represented by theta. Okay, it's theta in my case. So in our case, these both result, theoretical result and experimental result matches. So by doing this experiment, the angle predicted by theory, predicted by this, predicted is consistent with experimental value. Okay, so that's the reason this experiment confirms the dual nature of electrons. It behaves as a particle and also this behaves as a wave. Okay, so here this is a graph. In this case, for this given metal, for a scattering angle 50, we have intensity maximum. Okay, intensity is maximum. In my case, I just use angle theta in place of phi. So basically phi shown in the picture and what I used is theta is the same thing. Okay, so this experiment confirms the theoretical result. So from this experiment, we can say that the electron behaves dual nature. Okay, sometimes as a wave and sometimes as a particle, depending on the situation. Okay, so these are just for the comparison purpose. So diffraction pattern for the X-rays, and this is for the electron. So the observed pattern reflects the symmetry for the crystalline structure of the sample. So basically, both the diffraction phenomenon, either X-ray or for the electron, they reflect the same thing for the given crystal. Okay, so this is just a comparison kind of thing. Say, for example, in the Young's-Deboussy experiment, we'll find central maximum, then minimum and maximum. Okay, same thing we can observe in the simulation, computer simulated interference of electron. Okay. Now, let's move to spontaneous emission and stimulated emission. So, spontaneous emission means, say, for example, electrons, say, for example, in the, say, in the ground state, okay, and we have, say, this is excited state. So it could be anything. Say, for example, n, this could be n is equal to 1. It could be anything. Say, this is n is equal to, say, 2 or 3, whatever. If electrons are in the higher orbit, okay, they could jump to the ground state, giving energy of photon. Energy of photon is H equals HF. Okay. This is for the, say, first atom. This is for, say, for the atom first of an element. Same situation we can consider for, say, we have atom 2 of an element. Say this is the ground state, this is the first excited, this is the excited state. Electron could jump from excited state to ground state, giving a photon of exactly same value, E equals HF. But what is difference between this photon and this photon? Means their directions of emission is random, is not coherent. So there's a phase difference between the photon emitted by first atom and second atom. Okay, so this kind of emission is called the spontaneous emission. So there is a phase difference between the emitted photons from different atoms. So the sources behaves as a coherent. So for example, just for the note, we can say this has we have a 50-watt bulb, okay, and we have the other 50-watt bulb. Even though they emit, they are identical, they will not produce coherent source. So they are incoherent sources because they don't emit all light at the same times, even though they have the photon energy is same. Okay, so that's why they have, we can say this is we can say time lags between emitted photons. They are not emitted at the same time. So there is a time lag or phase difference. Okay, so this kind of sources are called coherent. This is called the spontaneous emission, and the sources are called the incoherent sources. Okay, for that region, if you remember in the Young's double slit experiment, what we did, we put one source, then we make up two sources. If you remember like that. So S1 and S2 are coherent sources. Okay, because it actually comes from the source S. I'm just talking about in the Young's double slit experiment. Okay, but instead of that, if you take two independent sources, okay, so here S1 and S2 are independent sources. Then in that scenario, S1 and S2 are not coherent. Okay, so this is just for the, this example is just for the note. Okay, purpose. Let's move further about the incoherent source. Sorry, about the stimulated emission. So we understand that from spontaneous emission, we get light in the random directions. So they are not coherent sources. So stimulated emission means, let's talk slightly different. So in the stimulated emission, okay, in stimulated emission, so let's see how it's different. So this is the ground state. Okay. Say this is the excited state. Okay. Say the energy difference between these two states, energy difference, say E, say just for example, say this is the second state, say this is your ground state, okay, n is equal to 1. If this is the case, then I can say this is E2 minus E1 is E1 equals HF, okay, energy HF. So say I have electron in the excited state. So if we strike this electron at the excited state with exactly same energy HF, then we have two photons. Incident photon, when this electron jumps to ground state, it also emits the energy. So one has energy HF, other has energy also HF. So this is the example of stimulated emission. Means this electrons in the higher energy state. So this is the initial position of the electron in the excited state. This is the final position. So now electron jumps from high energy level to low energy level, but in this case with the help of suitable energy. So that's why it's called stimulated emission. Okay, if you remember previous scenario, just is the recap. Your electrons is in high energy level, it could jump to ground state with the emission of single photon. Okay, but this is not coherent. This is the this we call it not the stimulated emission, we call it spontaneous emission. This is the spontaneous emission. Okay, still energy is HF, but different atoms emits frequency photons of same energy, but there is a time lag and produce incoherent sources. So this technique, stimulated technique, is used in the production of the laser beam. Okay, so it produces laser is a device that emits coherent and the monochromatic light. Okay, so the light is coherent if photons that compose the light are in phase. Okay, this is the key point, and it is the monochromatic if the photons have the single frequency. Okay, so to have the light coherent, we should have three conditions should be fulfilled. In phase, it should be monochromatic. Okay, monochromatic means single frequency. So to maintain the in phase, we should have the stimulated emission. Okay, so this is just a comparison purpose. For the coherent light beam, we have all are in phase. Okay, but if there is no coherent, means incoherent sense, they are moving in the random way. Okay. So if you understand that point, you can answer many questions. let's talk about the black body radiation. So this black body radiation basically also explains this black body radiation can be explained on the basis of the quantum phenomenon. Okay. So black body radiation also explains this behavior, quantum behavior. So in this picture, if you look at it clearly, you see that if temperature increases, say temperature start from like 2000 Kelvin, like 3000 Kelvin, 5000 Kelvin, you see that if temperature increases, okay, peak, for example, peak is here, peak is here, peak is here, peak for maximum intensity, we are talking about maximum intensity, shifts towards left, means left means a decreasing wavelength. Okay, in this picture you see wavelength increases towards left, towards right, and intensity increases upward. So we see that with temperature increases, the peak point shift towards left. Okay, so Planck's basically the Planck basically explains this black body radiation okay, for the first time. So what he did is this, is that according to Planck's hypothesis, energy emitted will be equals to integral multiple of HF. Okay, so this is the Planck's hypothesis. Okay, this is the Planck's hypothesis. Okay, this is the Planck's hypothesis. So once we used this concept, we'll figure out the result is that lambda maximum times T is always constant. Okay, so let us see in the here this value of lambda and this T, similar this lambda and this T, lambda and T product will be always same. Okay, so this value is always constant, is roughly 2.9 times 10 power minus 3 meter per meter Kelvin. So this result is called the Wien's displacement law. Okay, Wien's displacement law. Okay, and if we do after some math, we find that energy emitted will be I equals sigma T4. So in this case, this I is the total radiation intensity. Okay, for all colors. So This kind of black body radiation is explained on the basis of Planck's hypothesis. So let's, we can see one simulation over here. You can see the same picture that you see in the plot for different temperature. We can see the same thing in the simulation. If temperature is 8,000, you have peak intensity is 80. And we can find the wavelength corresponding is nearly 0.4 micrometer. If we change the temperature, you see, if we change the temperature, then we can find that the product of lambda, this product of lambda and T is always the same. So in this case, peak value decreases, but lambda value shift towards the right. Okay. So increasing temperature, the peak value is shifting towards right. You can see clearly over here. Okay. So you can play with these simulations. So if you understand up to this point, these are the not purely quantum, not purely classical mechanics. We are in the semi phase, half kind of thing. Okay. So we can discuss the failure of classical physics. Okay. And there are some resources you can watch, you can read. A lot of resources, very good resources are over here. So you can go over that if you want to go in more detail. Okay. Thank you.